just the same element, PE plus PS times times the cardinality of this thing divided by the cardinality of B, right? So it would be Q plus 1. Right? This group has the cardinality of B times Q plus 1. Yeah, this is Q to the 1. Yeah, that's whatever. And I divide it out, so I get this equation here, and so I find that PS squared is now well, I can look at my notes. This is helpful. I mean, I think it is I don't know. Maybe
QE plus Q minus 1 TS?
1 plus Q minus 1 PS.
No, technically it would be Q times TE.
Q times T, right? Q.
And
Q times T plus Q minus 1 PS is correct. Okay. So here we have here we have the multiplication rules of the second algebra. So let me kill everything here and write down the multiplication rules. So we have this Hector algebra of the with this, yeah. So this has a basis here x runs over the symmetric group, which I denote V, and we have Px dy equal to xy is the length up. And we have Ts squared is Q. The 1 is just Te plus Q minus 1 Ds if the length of S is 1. So okay. And now the thing is that we can check that these rules will give even an algebra structure if Q is a free parameter, right? Because I mean the associativity means then equations of polynomials which are valid at infinitely many Q's. So we just wanted also know. So we put here Q, and then this is called the generic algebra, the free variable. And quite often we put even Q to the minus 1 also, and some more things, and this comes later. No, not later. Comes right away. 2 minus 1 here, sort of always later. At least. Okay, so and this is then sort of something called the generic Hector algebra of the whole Riemann modulo. And in fact, you can do it on arbitrary complex system. And there's lots of calculations to do, but it just works. Okay. And now we are done with the Hector algebra. Well, almost. And now come these paternalistic polynomials. So So, well, this is a paper by Wolfgang and Jose. Yeah, no, no. So what they did, they defined an involution on the Hecke algebra, involution, and now let's see. I think it's if I recall everything correctly, you should well see for this business, yeah, for this business of the Hecke algebra of the Cauchy-Lüthy polynomials, it's much better to add a square root of for some reasons which will appear later. So let's add a square root and let's say v is v squared, let q to the minus 1. So this is a parameter. And inverse of the square root of q, I call it u parameter. And now let's see. I mean, oh damn how now because if I do something wrong with the parameters, it will sort of take me time to correct it. So I better wait for my computer. Yeah, here we go. So I'd like to use new elements because they are sort of I call them hx, which is v to the lx times t. Well, this is sort of the new basis. In fact, if you know something about covered sheets, and I guess you do, I mean these Tx would correspond to constant sheaves on these double cosets. And these things would correspond to constant perverse sheaves on these double cosets, moved in the correct degree. And this is why they turn out to be quite a good choice in discussing Cauchy-Lüthy polynomials. And then we define the duality on A.
Sorry. So you mean the perverse sheaf over G double set quotient by B?
Yes.
Okay. Just.
Yes. I mean. Yeah. It's always a problem. Yeah.
I get it.
You're right. You're right. It's a bit delicate thing. Okay. So I take the duality from the Hecke algebra itself. So this is the ring home, is it? Which takes v to the minus 1, or q to the minus 1, whatever. And these hx's will be meant to you take the x inverse and then you inverse the whole element. And for this to make sense, you certainly should check that these elements are actually orthogonal, but they are. And then you have to check that this is an algebra homomorphism given by these rules, and this is easy to check once you know the following. Once you know the following, namely, instead of these rules here, you could also use the rate relation ds ds is equals t s or t, yeah, t or s. Yeah, so there are these branch relations in the group, and these relations hold as well, and the hackathon they will also generate give a defined system of equations. Well, this is something that sorts of functional groups, and this means that uh, this means that. I hope it's now clear that these guys also satisfy the branch relations of these two. I think it's pretty simple. Just
May I ask a question?
yes.
So
yes.
the bright relation you mentioned here, do we ask about s? I mean, the length s plus length t is same as the length s times to t, or this bright?
Yeah, this.
Yeah.
Well, then the branch relation could end with an s and with a t.
Ah.
And I don't know how it ends, right?
Yes.
Oh. I mean, for example, they could read a ts equal t s if st is equal to s. And if sts is equal to tst, then the relation would be read tst is t. Like this.
Is this always no? This is not always
what?
So this st, of course not. So they're just saying s and t satisfying the following equation. Then we can deduce the upper equation.
Yeah. I mean, I should perhaps say that. I mean, this thing here is I'm doing it here for general cognitive group. I'm sorry, if just the symmetric group, it's only these the three-term or two-term relations.
Okay.
But if a general cognitive group, but that doesn't relation pretty much on.
Okay, thank you.
Yeah. And now I think I got the relation correct.
And so,
Yeah.
how are we treating V as an element of H here?
Yeah.
Yes.
Well, sort of formally, we should take here H tangent over ZQ with Z minus 1.
Okay.
Yeah. Okay. And then so we have this duality and we have to check that the H axes are all invertible. And so it's ring homomorphism and he square identity. I think. And let's see what HS where HS is mapped. So this H let's see. So what was we had here the equation ES squared is U plus U minus 1 S. So we would have HS squared is HS squared have to multiply with v squared. So it's 1. We have to multiply with v squared plus v minus v to the minus 1 a s. And I hope I got it all correct. This is terrible to calculate these kind of things on the blackboard. Yes. HS. I hope I got it correct. I mean, I should have that S. I should have that HS inverse is HS plus V minus 1. That's correct. Plus V minus V to the minus 1. Well, I mean, this is a bit nasty calculation, yeah? Which I don't want to do so much in detail. But the only thing which I really need is that the dual of H S plus V is plus epsilon. Which I think is hopefully clear from this equation. Well, you calculate, yeah? You calculate and I don't. Not here. And so for these Cauchy-Lucid polynomials, there is a theorem. Namely, so we could take an arbitrary Cox-Heter system now, or to take this magic group that we want. And then there is unique sort of for all x and it's the unique element of the Heter algebra with respect to this parameter V. And it has the property itself dual called Cauchy-Lucid self-dual basis. So V of H X is just itself. And it has the form that this thing starts with Hx, and then all the other coefficients are polynomials that are constant terms. And I think I want to ask, I mean, I need to ask nothing at all, right? So wow. So there is a unique self-dual element of this. And this unique and okay, I have to explain to why and how to calculate it. But then this self element, let me maybe discuss a bit its significance. Namely, this Hx could be written as so sum of some polynomials, yeah, H y x of v H y, and these things these things are sort of more or less Cauchy-Lustig polynomials, yeah? Cauchy-Lustig polynomials. I mean, Cauchy-Lustig has a slightly different normalization, so it's not exactly, but okay. And the significance of these polynomials is that now comes this question with different vectors. They tell that the multiplicity with which the simple subquotient with highest weight y of 0, it occurs in the Fermat modulus, so Jordan-Hölder multiplicity. This is this Cauchy-Lustig polynomial. Oh, now I've to check which one exactly it is, because I think it's just, if I recall correctly, yeah, it is hx y evaluated at 1. And so this was sort of a difficult theorem at the time. Now getting pretty better used to it, but it was pretty tricky, and all these perverse sheaves and intersection homology sort of was not yet developed, and they all sort of came together to solve this question. It was a pretty big breakthrough. Okay. But now let me discuss a bit why we have such a self-dual basis big, and why it is and how to calculate these guys. And so okay, so I want to discuss this theorem here, and now let's see. I claim the following. Yeah, I claim that if I multiply hx by hs plus z, two things can happen. Either I get xs plus hx times v. This is if x is bigger than x in the Breuer order of is long. And you know, if the things are longer, yeah, the hs times the x is just hx. If the lengths add up. But if the lengths don't add up, things chew up a little bit, and then you get still this leading term, but you get an x, which stays behind, multiplied by b to the minus. But this is you can calculate it. Yeah, I mean in the second case you have to calculate h, say zs times h s plus v, and then you get h zhs squared plus h s v. And now you know what hs squared is. and then okay, what else? And this means the following. So let me first discuss existence of these guys. Yeah. I mean, this. Well, we proceed by induction. Yeah, we start with HB, which we know is just H itself. Sort of this is already self-dual and has all the properties. And then if H, which if we try say if say X S is bigger than X, then we could write H. This we know by induction, and we multiply it with H S plus B, which is a self-dual element too. So this will be self-dual. And it will be of the form H X S plus so a sum of V Z V no V H Y, where Y is smaller than is smaller than smaller or equal than X. I mean, I want to prove existence sort of inductively, assuming that we know already we know already that it is given by Hx and sort of there lower down. And so if we have such an expression already and we multiply it by this other self-dual element, then the longest guy will move one up. Yeah, take xs. And the other guys, they have a v coefficient, and this v coefficient could get eaten up by the v to the -1 here, but it could never be a negative power. The power just can go down by 1. So we would find such a self-dual element, and then we can use the self-dual elements we have already by induction to put away the constant coefficients here. So we will have here, say, we can say this would be some plus say hy v, and then we get the UHSS by taking this expression, so X times S plus V minus the sum of the HY of 0 times the self-dual elements you have already by induction. And in this way, we have given an algorithm to compute such a self-dual elements. And now, to prove that they are actually unique, to prove that they are, just looking at the box at the time. To prove that they are actually unique, what we would have to do is to say if H is of the form some polynomial with non-constant term times H-wise, and the self-rule P of H is H, then it's here. Right? If we could show this, then we have to miss it. And and now the point is sort of by induction, we could express this. I mean, there will be a largest, there will be we could express this as a linear combination of the H-wise. And here are some coefficients, I don't know, A-y of the Z. And if we have the y, the maximal y with non-zero coefficient, then this coefficient has also to be in front of this guy. And then, because this is self-dual, this also should be self-dual and has only coefficient. So a contradiction, and this way we see that these guys are actually reduced. And I mean, usually I would just calculate an example, and maybe it's a good idea to calculate an easy example to see that this really an algorithm works. And maybe I do this before the division, and then I do that. So let me calculate some. Now this I didn't want to write. So to calculate, I want to calculate in the case of the symmetric group with 3 elements, and this is the reflection group with these reflecting plates, and I take this as a dominant chamber, and in this way, all the chambers are in projection to the elements of the group. Right? And now to write an element of a Hecke algebra, I just write its coefficient inside the chamber. Yeah, and then this way you can actually calculate. So I start with this picture. This is a P, which is the self-real element. And then I apply, say, the simple reflections might be S and P. And then I apply to it the simple reflection S. So I multiply with H, S, I have here this self-dual element. I already forgot it. I mean the self-dual element of H, S, which is H, S, D. And I know that if I multiply X by H, S, I get either H, X, S plus 3HX if X, S is bigger than X, and I get HXS plus e to the minus 1, X is smaller. And now this is the only thing which is very bad with my picture, that was smaller, it's higher. This is bad. Okay, we have to look at it now. Okay? Good. No, we have to look at it. Well, no, I draw everything like that. Too bad. So I apply now, I multiply with H. S, and I get this thing moves over here, and what stays behind, because I go down through the wall, it gets multiplied by V. And this is just the self-fuel element. Yes. Sorry. And then I go, now I apply the reflection P. So I multiply now with here I multiply from the right, but it's sort of no good because here I multiply, well, here it's still not visible, but but it's not honest. Okay, I do what I can. So I multiply now with HT from the right. Okay, now I have to be very careful. So this element is multiplied over here and gets longer, so I get a V square in the D. This element is mapped to this element. So it gets a 1. Okay.
Wait, it gets mapped under T?
What?
It gets mapped to the lower chamber under the actual wall.
Yeah, no, exactly right. This is my problem. I multiplied from the right. I should have done everything from the left. Maybe I change it because if I multiply from the right, then I have to move to the neighboring chamber under this. Which is bad. Maybe the pain is too big. Yeah, I multiply from the left. The pain is too big. So let's multiply from the left. Can you do it? So what happens then? Then I can really do what you want. So I have here this V which stays behind. And this 1 gets reflected over here, and behind stays a V. And then so this is all of this. There is no other ones appearing, yeah? So this is a self-fuel element here. This is a self-fuel element H underline T, H underline S. I think, yeah. And now I again multiply with H underline S from the left. Yes. So what happens? So I have this reflection. So this 1 gets copied over here and the 0 remains. This V gets down here and the V square remains. This V square gets down here and the V cube remains. A V cube remains. This V gets mapped over here, and the 1 remains. Because this V here is multiplied by a simple reflection getting small. And if it gets smaller, then we have to multiply with V to the minus 1. What stays there? So what stays behind is a 1. So this is a bad case where this expression we have here has here not only polynomials without constant term, but there is some constant term here. So we use the self-dual element we have already constructed to kill the 1. The self-dual element we have already constructed here. So we kill it away. And then we get the self-dual element all over here, which would now be so the self-dual element for STS, which would be the self-dual element for S times the self-dual element for S minus the self-dual element to subtract it, this one. So in this way, and you see now it looks that all these Cauchy polynomials would be very simple, but they are not. I mean, there's Patrick Polo proved the theorem that every polynomial with positive coefficients, non-negative coefficients, can appear as a Cauchy polynomial. So they can get horribly complicated if the group gets a bit small. And so can these multiplicities. And if you try to calculate that, you see there is these guys from the Atlas project in the States, and mostly it was Foucault de Clou, in fact, who is dead. He has a bad disease. No, and the problem with calculating these damn stuff is that you need lots of memory. There's sort of no direct formula. So you need to remember all the Cauchy polynomials which you have constructed before. Well, there's some tricks. You remember the glass, but now imagine you have a symmetric group with 10 elements. Yeah, it's the amount of memory you need, and this is a bit the problem. So now it's intermission until 35.
Maybe I can tell a couple of announcements. If people are interested in the algebras, there will be a talk at 4:30 by Simone Castellan. And on Friday at 2:30, there will be a talk by Filippo on nilpotent orbits and quantizations in positive characteristics. So if people are interested, there is other things to listen to.
Oh, wait. So today it will be where?
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 When is 16:30?
6:30.
Oh, yeah. To be C30. 60. Oh, 6. To be C60.
To be C6.
Oh, so there is plenty of room. 60 people fitting there.
Ah, this is the
number of
and who's talking?
Simone Castellani. About
Okay.
work with Prince Bellamy.
Okay, very good. I will go there.
And the other is on
Yeah.
Friday 2:30.
14:30.
Yes. In room 2. Do you remember? I forgot my glasses.
And this is on this post of it.
Yes. Filippo Ambrosio.
Filippo?
Yes, Ambrosio.
Ambrosio.
Here.
Okay. Okay, I have to check whether this is the time where I should be at the
stage.
Capella Scoveni.
Oh, no.
Then I think here this is the mic still all people although.
We can make a Zoom connection while you're watching the video.
Okay, thank you. Yeah, but the tradition until 35. Yes.
Before it's really was unusual. Something there. Yes. Okay. Let me stop the recording.
It works now.
Yeah, okay. Okay, now we have the Cauchy-Lucid polynomial, the Cauchy-Lucid conjecture. Now we need a proof. Now this is a bit of a problem, but okay. I mean, there are two quite different proofs. There is one proof, which is sort of original proof, when you use this localization technique. So you use the equivalence between category O and certain perverse sheaves on the flag manifold. And then the simple objects of category O has to correspond to simple perverse sheaves, which are the intersection combination sheaves of the real varieties. And the Werner modules correspond to standard sheaves, just constant sheaves extended by 0 on these flag varieties. And then in this case, in fact, already Kaplan and Lustig in their original paper proved that this intersection cohomology was described by their Cauchy-Lucid polynomial. And that's it. And now I want to stress another way to do it, which is sort of by causal duality in a way. So let me try to explain how this goes. And okay, this is also slightly tricky business, which gets us back to category O. Yeah, and the main player there. So we have this category O. And inside, we take the projective cover of the simple object of high flag minus 2 rho. To recall that we have in O, we just concentrated on this one block, the trivial, the principal block, and in there the simples were the L x dot 0, where x transpose y2. And there's one simple Werner module. So if we take here the longest element of the y group, then we get L minus 2 rho, which is also Werner. This is what happens if we dot the longest element of rho. And so the projective cover of the simple Werner module, this is this. And the first theorem, which now unhappily I cannot do for this. I mean, I have now to stop a bit proving, but I hope you will nevertheless be able to follow the factor of the thing, please. So the theorem tells that that the center projects onto the endomorphism rate on this antidominant projective. So it's called antidominant because this weight is sort of the opposite of dominant. This is center. So, yeah, certainly the center this is the center of the envelopment algebra. It acts on any representation. And here it just gives all endomorphisms of this guy. And more is namely, I mean, we have the Harshchandra isomorphism, right? Which well, the Harshchandra isomorphism identifies this with regular functions on page 0, invariant and the product, right? This is the Harshchandra isomorphism. And this we could embed into all the regular functions. And then we divide out the invariant under the by implication, but not dotted by implication. So it's modulo of there's so much to write. Let me just give this algebra another name, okay? So let me call this algebra R. And this goes to R modulo the guys of positive degrees invariant and as a while group, and the ideal generated by that. But here is the dot action, and here is the not dot action. And the claim is that this is also a projection. And they have the same count. Same count. Projection. And I mean this thing you might know. This is a description of the cohomology ring of the flag variety. Yeah, there's a Borel isomorphism. I should maybe repeat it, but this is the homology ring of the flag variety. Now with convex coefficient. Yeah. And so this is an algebra which is pretty well known and studied, and I usually denote it by C. And so this endomorphic grid of the antidominant project is this algebra C. Now, okay, this is already sort of a theorem, but let's check at least one case. Okay, I mean, I thought a bit whether I can prove it for you, but I mean, I don't know. I mean, it's time is limited. Time is limited, but let's check an example. And the only example I could come up with is SL2. Too bad. So this antidominant projective, we recall that it was given by sort of the swivel representation like this, right? Here was E and here was F, right? This was sort of, and then it goes down below. But what we now see, now we have the Casimir, which was also written T. Now this is bad, but what can I do? This is the Casimir, and it would be given. I think it was 4FE plus H times H minus H plus 2 maybe. Do you recall it?
I think plus 3.
What?
I think it was plus 2.
Here,
Yeah. No, it's correct.
Okay. Okay. And now look how this Casimir acts on this module. Yeah, the EF just match this to here. So it looks good, yeah. I mean the endomorphism of this, guy is just sort of the identity. Sorry, it's the basis, yeah. Identity and EN. And this cousin here, this letter part just kills everybody down here because this is H eigenvalue minus 2. But it's okay. So what we see is that the endomorphism ring of this is dual numbers. Yeah. So the endomorphism ring of P minus 2 rho is dual numbers. Yeah, it's something like C of I don't know what, maybe C modulo C squared. Yeah, some ring of dual numbers, two-dimensional ring, and there's identity, and then there's a Casimir, which does the trick. And I mean, this quotient also is just the quotient of the regular functions on the line by those functions which are invariant under making things negative. So this is what is written over here. Whereas okay, and yeah, and you see that so what happens here is that the center would correspond to regular functions which are symmetric at minus rho, whereas here we divide out by invariance at 0. And this is now some sort of algebraic geometry thing that this whole map has to be surjected. Yeah, because what can I say? I mean, why the third thing is rejected in general? I mean, I think it would be quite a general phenomenon that if you take take a vector space, yeah, and you have a finite group acting on the vector. Okay, it's finite. Acts on this vector space. And then the regular functions of V, say invariant under this action. Let's assume it's a linear action, yeah. And let's assume that we have a vector where the isotropy group is just here. So, and then the invariant functions would go onto the regular functions generated, divided out to the vanishing ideals at this point to any power. Well, so in our case, I don't know. I mean, here we have a reflection group, and we take invariant functions, and then we take some point which is sort of not fixed by anybody in the group, and then every sort of function germ around this point can be realized by an invariant function, because we can just sort of copy it to all of the. Can move it around in a way to get invariance. So I don't know. We can first take this function germ and take the zero function germs at all the other points and interpolate this function and then symmetrize it, and this will do the trick. So this is the reason why this is project. And but that it has the same kernel. This is sort of more tricky business. But and also that this is subjective. I mean, there's some tricks to be done, and I will not explain. But let me make another sanity check. Namely, what is the dimension of the endomorphisms of this guy? Okay. I mean, now I have a problem that I didn't explain you enough about factorial, but what can I do? I mean, I know that the multiplicity of a Werner subquotient of this guy is the same as the multiplicity of the simple Werner inside an arbitrary Werner. And now I have to tell you that this multiplicity is always 1. So here I have to take only allowed away, so the correct sense of character. So the multiplicity of the simple Werner as a subquotient of the Werner is always just 1. Well, some argument of scales and curve dimension, whatever. So here the Werner subquotients are always just 1. So I know that this is the multiplicity in this module of this simple module it covers, right? This formula we had for more general case last time. And this is the sum of all x in the y group of the Werner modules and the Jordan-Hölder multiplicity of this simple guy inside. And this is always just 1. So it's just the cardinality of I. So the dimension of this endomorphism is the cardinality of the. And the dimension of the homology black variety, you know it's the cardinality of the variety. Because the Breuer cells that form a cell composition. And they're only even dimensional cells. So at least the dimension of these two things are the same. And okay. But to really prove this, I don't know. And okay. And now comes the next theorem. And this I really discovered at some point, and I was very proud of it. Namely, when you have say an arbitrary, you have two modules in the category O in this graph. And the second one is projected. Then we get an isomorphism between, let's say, homomorphism in the near blocks of M to Q. and therefore isomorphically to homomorphisms over this ring C, which is this ring. Yes. Of Vm Z2. And V is just homomorphisms from this anti-dominant projective to something. Yeah, you can take the homomorphisms from the anti-dominant projective to something, then this will be a module over the endomorphism ring of this, which is C. And this was sort of the big surprise that this map would be an ideal physics. And so, in particular, what you can deduce from it is corollary. That the category of projective objects from OD plus, this gets fully faithful to C1. Right? It is, right? So finite dimensional well, right off. Just modules over this homology rate. And this is just this functional field which gives a fully faithful embedding here. And so whenever we have a indecomposable projective guy here, it gets to an indecomposable projective C modules. I call it X. Yeah, this is an indecomposable C module. And now the question is, which C modules are they? Huh? I mean, I call them just special, yeah? Special C modules. Absolutely special. And if you know these special modules, yeah, then you know the homomorphism, you know all these projective guys, and then you know the whole category. Yeah, and so let's do it for SL2. Yeah, just for the fun of it. So what will happen for SL2? Well, so if the Lie algebra is SL2, then this algebra C is, let me use some variables, yeah? Okay, P modulo Q squared. Yeah, it's a dual numbers. And there is one special module which is say the trivial. There's this projective which is just the Raumeier. It is just the Raumeier. This is already projected. And this is well, C. And V minus O, which is minus O, okay, so whatever, and this will be the whole ring C. So this is the special bimodule DE, and this is the special bimodule DS. And sort of this whole, so in fact the whole category of O, in this case, will be either more equivalent to the modulus over the finite dimensional modulus over the endomorphism rate of C plus C. So now you have to look that this is really the correct quiver and why is all this, but I think my time is up. No, wait, no, until 10 after.
10 after, yes, 10 minutes.
10 after, I still listening time. Okay. Okay, because I think I didn't quite explain this. I didn't quite explain this enough, please. And this is another business where I thought, whether I can prove it, I'm not sure. But I mean, let me first discuss part of what part of all this is easy. Namely, say if you have A, then I really something. Category, and every object has finite length. Finite length. Object. And now projective. Objective. Let's assume this, and let's assume we have here what's called a projective generator. So projective generator. So it has a non-zero map to every object. Yeah. So I could say surjects onto every symbol. Onto all symbols. If we have this, then there is a general theory which tells us that the category A will be equivalent to the category of right and modules of finiteness. And the functor is taking homomorphisms of P to something in S. This is sort of a general nonsensical stuff. Yeah, the functor will not kill anybody, and we have an adjoint functor. That adjoint functor is something like tensoring with P. I don't know. I mean, some business. Maybe I forgot something, but I don't think so. I think I was very careful to make finite length modules only. Yeah, because the right finiteness conditions everywhere. And this is what I find here. So in particular, if we want to apply this to category O, then we know that where could I write this? I could kill this, yeah. I could kill this. And I could say that this category O plus will be equivalent to modules of finite dimension over the endomorphism rate of the direct sum of all these projective guides, indecomposable projects. The sum of all these indecomposable projectors will map onto every simple object. And okay, I could take one of these several times, yeah, but I cannot miss any one. And so the equivalent category. And because I know that this is also the same thing as the endomorphisms over this algebra C here of the direct sum of the P. S dot 0. Right, so here I have a nice description of this category. Oh, if only I knew what these special modules would be. Yeah? But in this case, I know what the special modules are. It's very easy. Okay. Now, what else to explain? Maybe now I can. Now it's not the time for technicalities. So let me explain how you can get a hold on these modules, sort of brutally, namely there's sort of a companion theorem. There's a companion theorem which says the following. So now we take a D1 and inside we have this real cell, and we take its closure, and this closure has an intersection congruently complex. The pervert sheaf on the flat rock here. And this intersection congruently complex has a hypercommon, which is, I don't know, I see. And this, in fact, is a module over the homology of the flat rock. Wow. Okay, complex. Module in here. And the claim is that this is the same. Okay? So that this is in fact now I have to be careful. I should take x dot now there's a question about whether I should take an inverse somewhere. Let's see. If I have x as unit element, then I would just get C. And here, if I take just the gamma module, so it looks good. It looks good. So this SC module. C module. And now the trick is that when you know this, this gives another proof of rationality conjectures. Yeah, you can use your knowledge about ice intersection homology complexes to determine what these modules should be, and then you can sort of fight your way up to know what the projectives should be. And if you know what the projectives are, you know the Jordan-Hölder by reciprocity. So this is another way to fight your way up to get the rationality conjectures. And now the wonderful thing is that Georgi Williamson even found a proof of what these bimodules should be, which doesn't use rationality, sort of arithmetic geometry, just sort of combinatorics. So I could even prove it without arithmetic geometry, which is sort of even better, but still too long to explain it here. So thanks for your attention.